Hello everybody, and welcome to today's lecture on interpolation methods in chemistry. This is the fourth on the numerical details, and again let me start off with explaining why do we care. Now, if you think about interpolation, what it's really good at is you have a few points, they span some domain of a function, and now you would like to get a reasonable estimate for the points in between. And what is reasonable kind of depends on your problem definition. Let me maybe introduce two families of problems where this is commonly used. So for example, if you have the potential energy surface, so how does the energy of a molecule change if you were to change its geometry? And the problem is that evaluating this rigorously is fairly expensive. So you want something that can make life a little bit easier in that regard, and at least gives you a quick estimate of what the real value could be. And more often than not, this actually turns out to be a pretty good estimate. So the idea is you have this potential energy surface, think of a bond stretch, and you just calculate this in a few points. But now you would like to know what's the intermediate value on one of those geometries. So that's one example, and we're going to look into some numerical details for that later on. The other problem is you have, for example, experimental data, and you would like to have a simpler, interpretable representation of your measurements. So for example, if you have if you were think of a bond potential, and then the curvature of that bond potential at the minimum relates to the force constant that acts on one particle, which again tells you something about vibrational frequencies in that. So if you were able to actually measure that, what you want an estimate of a local curvature. For that, you very likely have to smoothen the experimental data points you have, or whatever reference data we have, in order to reduce the dimensionality and just look at this one stretching motion. So whenever you have maybe a random scattered set of points, you would like to have some curve fitting in that regard, then very likely you're going to need interpolation. For example, if you do experiments on liquid gas phase mixing, then again you often have the case that the actual transition between the two is not really observable with common techniques. So you have this domain within which you have no measurements. You have a measurement where it's clearly liquid, you have a measurement where it's clearly gas phase, but you don't have anything in between. Now, the data point you're most interested is the one that tells you when the phase change happens, and this will require interpolation. So you take both measurements informations you have and then interpolate the one point you can't get, but the one point that you definitely want. So for that, again, that simply requires to use data points you have and then interpolate between those. Another reason why you might use that, or the interpolation method, is if you need to evaluate a function very often that in fact is expensive to calculate, but you still need it frequently. For example, if you think force fields, then many force fields are based on custom functions. For example, for carbon compounds, there are special force fields, and some QM codes, for example, or some MM codes allow you to enter this just by its functional form. And evaluating whatever you wrote each and every time is slow. So what they do is they take your function, which can be arbitrarily complex and arbitrarily expensive to calculate, and they take the domain over which you're interested, for example, typical bond distances, and then they evaluate the function on several points along the way and interpolate between those, and use the interpolant to actually run your calculations. This, for example, if you consider exponential functions, unless you have very recent hardware, exponential functions are expensive to calculate because technically they require serious expansion, and this takes significantly more than just a few multiplications. And that's the reason why people, historically speaking, avoided exponential functions at all costs. We talked about the Lennard-Jones potential last time. But effectively, when you have such an evaluation, then that becomes expensive fairly quickly. And you can also think of an expression that is ill-conditioned, so where numerical imprecision of the calculations plays a significant role. So then you could go ahead and with NP Math or Mathematica or whatever you like, calculate the correct value at arbitrary precision, which is expensive, and then interpolate between those values using the interpolation techniques we discuss here. So whenever you want to reduce the computational cost associated with a function evaluation, then this interpolation technique is one way that you can follow. And the beauty of this approach is that it allows you to look at the actual coefficients, what they mean and what they tell you. So often individual coefficients of curve fitting actually explain something, have a physical or chemical meaning that you can connect to. So the curvature of potentials is related to the force constant, and hence gives you vibrational frequencies. Or for example, if you look at the path the particle takes through a liquid, then this is the particle diffusion part, where the diffusion coefficient is related to the slope of the mean distance. So in those cases, every time the coefficient that you get from fitting or from interpolating the data points you have might carry a significant meaning. That's why it's often advantageous to use that fitting or to use interpolation techniques. So how would you do it? And I would like to briefly talk about two different families in that regard. So in the same way as we had the optimization, where we have something that works reasonably well for lower dimensions and something that works reasonably well for higher dimensions, again, the same concept here. So for low dimensions, and low dimensions in this case means 1 or 2 deep, there are several approaches that work, and they're mostly tailored towards accuracy. Because the main fear in interpolation, of course, is that you get something which is vastly different or sufficiently different from what you're actually interpolating, such that you get deviating results based on any calculation that you do with the interpolant rather than with the free correct function. So the 1D case or the 2D cases, people tend to be very thorough and careful on how to make this work in the most accurate way possible. That's also because cost usually isn't a matter in 1D or 2D. But the moment you look at a higher dimensional case, starting at roughly 3, you are paying dearly for that accuracy. And practically, you wouldn't use most of the methods that you have for the 1 or 2D case in higher dimensions, even though it's often technically possible. It's just awfully slow. So this scales very quickly. That's why they're basically these two kinds of families, because in the higher dimensional case, all the algorithms and methods are usually designed for speed. And in the lower dimensional case, they're usually designed for accuracy. And of course, that's the consequence of the no free lunch theorem that strikes again. Okay, so let's have a look at this lower dimensions of the 1D case, as I called it on this slide. And the typical idea behind interpolation is, again, to use polynomials. And why is that? because polynomials are nice, they are described by few coefficients. They can be derived arbitrarily. They have nice properties. You can express many of its combinations or of the arithmetics behind by matrix operations. So people like to use polynomials. And again, they are piecewise. So for every segment of your data point, you have a new polynomial. And the same way as when we discussed numerical integration, where we've seen that there's a significant numerical instability if you were to use high order polynomials. That was called Runge's phenomenon. And then you have, in principle, you have the same problem here. You don't want to have one polynomial that covers everything and then interpolates through everything, but you'd rather have something that is of low degree and then different segments. And a typical way of doing that is to use cubic functions, because cubic functions have nice smoothness conditions. We're going to talk about that in a bit. And in those cubic functions, you interpolate between every data point. So you take all the input data that you have, all points along, for example, the x-axis, and then for each interval that is formed by these points, you devise one polynomial that is meant to cover the intermediate points. And typically, not always, you recover the exact points that you used for your fitting procedure. Whenever you are at that x value, you get the precise y value to go with that. So it's mostly cubic functions, not always, but I will discuss the main flavors in that regard. The nice thing about polynomials, as I mentioned before, is that they are differentiable. And if you have these piecewise segments of the total domain, of the total interval over which this interpolant is defined, then you can connect these segments. So the idea is that you make sure that there is no sudden jump in these polynomials. You make sure that, for example, the first derivative of one segment at the end point is the same as the first derivative of the next point at the beginning. This way you make sure that this gives you some kind of smooth function over the whole interval. So the fact that you can get nice derivatives and that they again are expressed in just the coefficients of the original polynomial is the reason why they're so popular, because then you can easily define those boundary conditions. So every segment has its boundary conditions to match the next one. And depending on what order you have and depending on what kind of polynomial you use, different of those conditions are used, but the overall idea is to have one totally connected set of piecewise polynomials. Of course, one of the considerations in this case is that these simple functional forms are fast. To evaluate a polynomial is pretty easy. In particular, if you use the binary exponentiation that we discussed last time, there are several tricks you can do in order to make polynomial evaluate very quickly. And that's in fact something that is exploited commonly in this case. So you get pretty astonishing accuracy just based on those polynomials. But keep in mind that, of course, this depends very much on the function that you look at. We're going to see some examples for that. In a higher dimensional case, now the problem is, if you were to fit something, imagine you were to take this polynomial concept and say, I'd like to have this in 5 dimensions. Then this becomes painful very quickly. Because now you have to, not only you have to have all those derivatives in different directions, but you also need to match all of those, which means that the number of coefficients explodes quickly, and your overall system of equations that you need to solve becomes large as well. This is a pain. So I think Python, the Python interface that you have in scipy can do B-splines until 2D or even 3D, but at any higher dimensional case, even if it were implemented, it's going to be painfully slow just because of that reason. So one of the tricks that people use is that it's maybe a bit counterintuitive, but if you go to a higher dimension, then things become, they converge to unusual cases very quickly. Maybe to make this a bit more precise, if you pick any nearest neighbor in a high dimensional case, then the volume that each individual nearest neighbor needs to cover becomes small very quickly. So just after a few dimensions, this converges. If you did the exercise on numerical integration, the one where you calculated the volume of a 5-dimensional sphere, then you might notice that if you plug in some higher dimension, that this thing becomes small very quickly. So it's actually the volume of an n-dimensional sphere has a maximum, I believe, at six dimensions. And afterwards, it just gets smaller. Just the same way as if you take a random vector in n dimensions, it's almost always orthogonal and only rarely non-orthogonal. So it's an interesting thing that if you go to higher dimensions, basically what is considered to be common is completely different than what we're used to. That's why in very high dimensions, actually nearest neighbors nearest neighbor values are not that bad for interpolation. But they're so cheap because all I need to do is calculate the distance to other points, and this is a very efficient calculation. It's just the L2 norm or whatever other metric you come up with. And there are clever ways how to make this evaluation be fast. So in particular, in very high dimensional space, maybe 10 upwards, nearest neighbor values are very hard to beat. So that's a common trick in that case. Now, if you say, I'd like to have it accurate, so not only fast, but also accurate, then there is a clever way of doing that. It's basically putting basis functions at some point in space. You can imagine as if you were to put a Gaussian somewhere in your high dimensional space, and then say that this point has some impact around, or the value at that point has some impact in the vicinity thereof. And then you do that for all your data points, and then what you do is you calculate the value, you optimize coefficients in front of those Gaussians, but then you can calculate the value by looking at all pairwise distances and then just sum things up. In just functional, in an interpolation community, that would be the radial basis functions, which are implemented in scipy. I just said right away, it's gonna be slow again. The main reason for that being that you need to compare lots of distances. The implementation in scipy doesn't have something like cutoff schemes or k-trees in order to make the evaluation cheaper. It's just a plain and simple pairwise distance calculation. And of course, if you have, you need very many points in order to cover a substantial amount of the space you're interpolating, because it's called interpolation, so only between points you have. And therefore, your distance evaluations that you need to do become plentiful and therefore slow. So this is hard to accelerate. It's possible to do that. scipy doesn't do it. This conceptually is very close to the kernel ridge regression picture that Anders is going to talk about in the machine learning lectures. There again, you have the same concept in some space. You place kernel functions, for example, Gaussians, on individual points, and these Gaussians, they measure how far this value stays representative for other points in that region. But this is a fairly advanced technique of interpolating in high dimensions. So the problem is that you can't really transfer this picture of things being equal, where if they are close by, into high dimensions, because as I mentioned before, what is close by, the volume of that becomes small very quickly in high dimensions. So the main question is, if you do the interpolation in significantly more than 3 dimensions, you might want to carefully check as to whether this makes sense at all from the function that you have, because if the volume that one point represents in this high-dimensional space is just so small that your typical query point would be far away, then it makes no sense to interpolate, because the underlying function could have done anything in that small additional distance. So interpolation in higher dimensions is tricky. So that's why we're going to focus mostly on the 1D and 2D case, which are also the cases which are most relevant to the day-to-day work of chemists, be it experimental, be it theoretical. All right. So within these 1D and 2D functions, within that class, there are subclasses. And the first one is the distinction between an exact interpolation and an approximate interpolation. If you look at the figure on the right side, here we have some x value and some associated y value, which would be our functional form, and we have these blue points. So these blue points are actually evaluated functions. So we know the exact value of a function exactly at those points. What we don't know is how the function looks like in between. Now, the interpolation problem would be exactly to find some smooth connection between those points such that the interpolation becomes a representative or approximate of the underlying function. And if you make sure that things are exact, meaning that at those points that you have, you recover exactly the y value that you plugged in. So here, if we have 5 and 5, then any exact method is going to yield 5 if your x value is 5. And it's going to yield 8 if your x value is 0. So the beauty of it is that you don't see any problems with this fit if you only look at the points at which you have actual data. Now, the problem is that this is often prone to overfitting. Imagine each of these points would be subject to some noise. This would mean that these points would move slightly upward or downward, and this is going to disturb the interpolation. This is, I'm going to show you some example of how severe this can be on the next slide. But effectively, the exact methods, they are usually only helpful if you can be very sure of your functional form. So if you know that this y value over here is not something that is maybe subject to experimental uncertainty or subject to numerical artifacts, but this is the true value. There is only 5. And only in those cases, the exact interpolation schemes actually make sense. So this is what you have here. This S value is a so-called smoothing value in the context of B-splines. We're going to talk about that in a bit. But here, the main message is if S is 0, then the B-splines become exact. So they go through all data points. And as you increase S, they are allowed to deviate more and more in order to reduce the curvature. So you see that as you go from the blue curve, which is the exact B-spline, to also the cubic spline, to a smooth version where you have S is 0.1 or S is 1, things become more smooth. So here, the green curve undercuts the effect of the Y and does the same on the other side over here for 10 and 15. So effectively, this means that green is more or less, say, inspired by the blue points, but not driven by the blue points, whereas the blue curve with S is 0 goes exactly through all points. So orange and green would be an example of the approximate class, where you say you try to be close to the points that you have calculated, but you don't try to be exactly at those points. And that is particularly helpful if you have numerical noise. So if you want to be thorough in that regard, there's actually a way to relate what kind of S value you should have here in the context of B-splines. There is a way to relate that to the numerical noise that you observe in your data. So if you know about the uncertainty of each individual data point, there is a way to calculate what kind of S value and what kind of individual weights these points should have in order to recover the best interpolant of this. But this is fairly heavy, so I will not go into detail on that. So effectively, another way of thinking about that is, in particular if you consider the machine learning picture, is Sx as a regularizer. So as you increase S, you force things to be more smooth. And this would be the same thing as a regularizer in other methods. For example, in least squares fitting, again, you can do that. If you have an overdetermined system, you can use a regularizer to make this less prone to overfitting. And the same concept is the meaning of S over here. Of course, this bears a significant risk, because even if I do derive my S in a rigorous fashion and estimate what kind of smoothing parameter I should have in order to deal with a given noise level, you run into the risk of overly simplifying things. I mean, you can easily imagine if I make my S very, very large, then what I get is a horizontal line. And that's not representing the points at all. So in that case, this means it's a danger to just crank up the S in order to make the picture nicer, because things are more smooth and less jagged. But that's the wrong way of doing things. You should have an estimate on the S, or at least the motivation on that. And one way of doing that, if you don't want to do the rigorous picture, is to take the uncertainty data you have and use that noise on some test function, say quadratic function or something like this. Just add the noise and then check for the S value such that it recovers the original functional form that you have put in. That's an effective correction to that data that you could have. So the key takeaway message on this is, if you trust your data, then you may use the exact case. If you don't trust it that much, you might want to check out the approximate family, but you should be careful as to what kind of error this introduces by oversimplification. Now, I would like to talk about this overfitting point a little bit, because it's not completely obvious why this is a problem. Now, of course, you can just say, what happens if I just have some small jitter on the data points, if they are moved out of the equilibrium position just ever so slightly? Does this give me like deviations? Why is this bad? And the main reason for that is, again, the high order polynomials. If you look at the figure on the right first, then again we have our blue points. And these blue points are approximately following some quadratic function. In fact, they are a quadratic function with a gap in the middle and some numerical noise that gives us the deformation in between. And now the problem is that if you, for example, pick a polynomial in interpolation polynomial with a high degree, then this means that you can fit any point arbitrarily accurately. And that's the red line that you have. This is, I think, 11th order. And you see that going to higher order does not make things better. So even in the regions where you would expect things to be nice, so neither the boundary nor the gap, just somewhere in between, on this end you have the significant deviation, and on this end you have the significant deviation, which comes from the fact that you're overly trusting towards those data points. And in particular, if you have these a slight zigzag pattern of an error going up and down with respect to the true function, then the high order polynomials will do exactly this. They will go in strong oscillations through those points, and that's exactly Runge's phenomenon. So what you want is not mapping each and every point individually. What you want is mapping the effective underlying functional form. And that could be, for example, this quadratic fit that you have here. That's the green line that goes through that and gives us a decent estimate here at the peak at 0. Whereas the high order polynomial does not, because obviously this red line makes no sense whatsoever. And the same you have if you just were to use B-splines. I'm going to talk about that in a little bit. If you just were to use B-splines, and that's the blue line in between. So you see it looks all nice, but it also goes through all the points. And most importantly, it's kind of confused by these two data points here, because this data point has a random error pushing it above the quadratic line, and this has a random error pushing it below the quadratic line, meaning that this change in curvature is recovered by the B-splines, and since they have no regularization, since this is the exact interpolation, then this means that you get this significant deviation. So at every point, your life is nice, but at intermediate points, the numbers are significantly less reliable. So for example, what you see here is, in order to complete the discussion of the picture, we have some quadratic fit, which is just one quadratic fit to all these data points, that's the green line, or we can have a regularized B-spline, so where we use the smoothing factor that I've shown on the previous slide in order to get this to a more effective shape, which also makes sense depending on what the problem is you're looking at. So in both cases, you see you get a nice, well-behaved peak in the middle. You can argue about which value is correct, but this, of course, depends on your application. But I think we can both agree on the fact that this blue line and the red line don't make sense in this context, mostly because this is just overly depending on these 2 points. If they were the other way around, then the blue line would deviate towards the top. So the key message, I believe, is don't ever try to use higher order polynomials for fitting in an attempt to make things better. Now, I've seen plenty of published papers where people do that. Please don't be one of them. So effectively, the main trick is to either have a better insight as to how this functional form should look like, and you can do curve fitting directly. So for example, if you have a bond potential, you could say, all right, I'm going to fit some Lennard-Jones or Morse potential to it, and that's going to be more accurate in estimation, because you have an underlying reason why this functional form should be relevant. If you don't, then the best way would be to say, let's look at interpolations. And for example, there's B-splines and C-splines, and I'm going to explain them on the next slide. So the B-splines that you see here, that's the blue one. They come in an exact fashion and they come in a regularized fashion. And these B-splines, they are typically very well behaved, but they are sensitive to noise level, to noise changes that you can have. The nice advantage of the B-splines over other methods is at least they have fewer numerical errors. So for example, if you compare the high order C-splines in here, that's the red curve, with B-splines in that case, they are more well behaved, but in the end, they're still prone to the individual noise. So if you can't trust all your data to arbitrary precision, then in practice, what you very likely want are either regularized B-splines or C-splines, and the regularization is more reliable in the context of B-splines. Okay, so I've been talking about B-splines and C-splines. Let's have a look at what does it mean. So those are, in fact, representatives of the two main families that you can consider. The C-splines are typically the representative of calculations or of interpolation schemes where you have one fixed polynomial of nth order, for example, of third order, then you have cubic splines, and then you match those derivatives as you go through the individual data points. So in this picture, you would have one spline from here to here, and then one spline from here to here, and then at this point, you make sure that, for example, the first order derivatives are the same, and that the y value is the same, otherwise you'd have a discontinuity. And this is often called to be n-smooth, where n is the number of derivatives where things are still continuous. So this is what I show in this figure. So again, the data points that we have here are exactly the same data points we had on the previous slides. And the blue line is the so-called clamped C-spline. I'm going to explain this in a little bit. So this is the cubic spline that goes through those points. You can already see that the cubic spline here and the B-spline over here, they differ in their interpolation. So it's not unique. For every method, there is typically just one interpolant which is unique, but the individual methods, they can differ quite substantially. So in this picture, what we have here now is this interpolant, and it looks quite nice and smooth, but now we can look at the derivatives. I mean, it's polynomial, so I can easily calculate the derivative. And this is what we see here. So the orange line is the first derivative of this function. So it crosses 0 at this minimum, and it crosses 0 again at that maximum. So this orange line is exactly the first derivative. And you see it's perfectly smooth. So there is no discontinuity, no jump. And it's also of constant smooth connections. So it's differential everywhere. Whereas if you look at the second derivative, that's the green line over here, you see it's linear in every curve segment. Most notably, it's not differentiable at each individual data point. And that comes because you just run out of coefficients. So since you have these discontinuity, since you have the continuity conditions such that this polynomial must match this polynomial, and each of these polynomials just is of order 3, this means you have 4 coefficients. Because for each power of the polynomial, you have 1 coefficient, so that's 4. You need 1 to map the boundary condition on the left side, so just the vertical, the y value. You need 1 to match the same on the right side of each polynomial segment. And if you now want to make sure that the first derivative is the same, then that costs you 1 more and 1 more, so you are already running out of coefficients. If you want to make sure that the second derivative is smooth as well, then this would require that you go to higher order. So you can do quartex splines. It's the same concept. You just have a 4th order polynomial between the two, and then suddenly you can make your second order derivative differentiable again. Now, of course, the problem is, as you go to higher orders, you also are prone to get this Runge's phenomenon with the wild oscillations around those data points. So that's why typically cubic splines are considered to be some kind of practically reliable sweet spot between usable enough, but also low order enough and numerically stable enough. Maybe in contrast to all these numerical integration schemes that we talked about, there is no requirement for the spacing of the points. So in principle, these can be arbitrarily spaced. They don't have to be evenly spaced. There's just one thing you probably want to consider if you have very dense spacing. Most importantly, if you have spacing that is so dense that the y values, just by numerical noise, can be slightly different And this difference becomes significant on the different x values that you have, effectively meaning if 2 points are very close, but their y value might be significantly different due to numerical noise, then you're going to get wild oscillations between these two, just because of the derivative mapping. And this applies even if you use lower order polynomials. It's just because it needs to match the derivatives for those close line points. So in that case, you want something that can be regularized, that can get some well-behaved data points. So the key message is maybe cubic splines work very well if you can trust those points, and if the domain on the y-axis is substantially large. If the domain on the y-axis is pretty small between neighboring points, and this becomes numerically unstable very quickly. So typically cubic splines don't get better by adding boatloads of points. They are very helpful if you have a large domain to span and just a few points. So that's the limit where cubic splines make no sense. If you consider B-splines, their idea is a little bit different. Their idea is to minimize curvatures, and they have, again, an order, depending on how many, what kind of order you would like to have for each of these polynomials, but their idea is they're inspired by the functional form or by the shape that, for example, the bendable stick or ruler would have if you were to make it match all the points. That's historically where they come from. And these individual data points that you have, they are not really data points, they're called control points, meaning that they give a hint how the function should be aligned, but typically there is no strict requirement to actually recover that particular data point. You can have it, that's this S is 0 case, but the main concept of the B-splines is that you can make it, that you have this gradual way of making things smoother by increasing that point, or this smoothing factor. So let's talk about the same thing. So again, we have this B-spline. You see it looks different from what we have here. So which one makes more sense is something you have to decide based on your application. But now you see the first derivative is this one here, the orange line again. And also the second derivative is smooth. So what does it tell you? That tells you that the B-spline, the function behind, at least has to be of order 4. Because for B-splines, it's the same concept. You match the derivatives between the individual points, and again, you have no different spacing of no requirement on the spacing of the individual points. For B-splines, there's problem of having 2 points close to each other, but some error noise on those. This error is less problematic with the B-splines, because even if you just put a very small non-zero value for the smoothing factor, then the resulting B-spline will hardly be affected from the numerical noise. So whenever you have something that is to some extent noisy or can be considered noisy, I would suggest to look into the B-splines, which also are more well-behaved if you think 2D than cubic splines. Both are implemented in scipy. Let's maybe talk about the overall Python picture on how to do that. So again, scipy has these different submodules. We had optimize from scipy, we had integrate from scipy, now it's scipy interpolate. And this interpolation part of scipy has a little bit confusing setup of ways how you can implement things. So they have different interfaces, the same as the optimization module, which all effectively do the very same thing, just based on different libraries and with a different degree of adjustable things. What we will discuss in the lecture is just, let's say, the surface, the highest level, the most abstract level of this interface that SciPy has to offer to get started. But if you want to go into details, and particularly if you want to fine-tune B-spline interpolation and make it fast and efficient, there are special functions that allow you to do that. They are also part of the SciPy interpolate module. And I strongly recommend that if you use B-splines regularly in your day-to-day work, that you check them out. What they're doing, they are again based on some, I don't want to say ancient, but let's say aged Fortran library, which is highly reliable in that case. So I strongly suggest if you have a tough interpolation problem, check these lower level functions out for solving a problem. So again, SciPy gives us these two families, the cubic splines and the B-splines, and for both of which I would like to walk you through some code example. We have our data points here on the right. It's still the same data points as before, but let's have a look at how you can work with this in Python. Let's have a look at the code at the left first. So at first, we need to load SciPy interpolate. Now we do that, and I like to abbreviate that, otherwise your code is going to be littered with SciPy interpolate everywhere. So again, we have this abbreviation, and we load numpy just as before. Now we have some x and y as values. Those are just the values behind these points. And if you maybe focus on this line first, so where the red dot is, then this is the idea. You get some object, the C-spline object, which you build by calling cubic spline, and you give it the x as value, the y as value, and some argument that specifies the boundary conditions. And what you get is this object here, C-spline, this variable, which you can use as if it were a function. So it's callable in the Python picture. So if you have some value, say 5, and you would like to know what's my C-spline value at 5, you just call C-spline of 5. So instead of XSS, you would write 5 in this position. And this is a fairly convenient way. That's why we have the other code around that. So the XSS, that's the way how I like to refer to intermediate points for visualization, is the linear distributed points from 0 to 20, namely 100 points on that space. And then I plot first the original data points with a scatter function, and then I plot the XSS and the C-spline value at all those points. And this way, then you get all the intermediate points to visualize those. So in that case, so for the naming scheme, I like to do that because then XS denotes that it's multiple X values, and Y as the same, and then add an additional S for interpolant values. Now, keep in mind that this is an object, so you don't only have the option to write C-spline and then call it with some position at which you like to evaluate it. It also has more options. So if you look into the documentation of SciPy cubic spline, then it's going to tell you that, for example, it can get you the derivative of the spline, it can calculate roots of the spline, it can integrate it. So any of those methods can be very helpful. In fact, one of the exercises is going to look into this part. Now, we haven't talked about this thing here, the boundary conditions. And the boundary conditions, they make sense if you think back to what an interpolation spline actually does. At each point, it matches the derivatives of the polynomial before to the derivatives of the polynomial after. But at the edges here, there is no polynomial before. And at this edge, there is no polynomial after. So we need something to substitute for that. And this, in fact, is what we have. This is the boundary conditions. So this stands for boundary condition type. And there are a few popular solutions to that problem. These are the ones that you see here. So they typically mean, for example, clamped is that the first derivative is 0. That's why this thing flattens off towards that data point and does the same over here. So the idea is at the individual endpoints, you force the first derivative to be 0. Then there is the not approach, which assumes that the first and second polynomial are the same. So effectively, this makes this data point here not a knot of the individual C-spline. And again, it does the same thing with this one, because from the right side, this is the first polynomial, this is the second, and this one is the first, and this is the second from the left side. So in the not conditions, these 3 points define one polynomial, and these 3 points define the other polynomial. That's, as you may have guessed, only useful if you have a substantial amount of data points in the middle, because otherwise you're mostly governed by these two outer regions. That's why you see that not is substantially different from the other two solutions, in particular in the outside regions, because there's no additional polynomial in those regions. Nonetheless, this is the default concept of scipy. Then there is something that's called natural, and the idea is you're not forcing the first derivative to be 0, you force the second derivative to be 0. Which one makes most sense depends on your particular problem. There's one special case that you can use. If your problem is in fact periodic, so for example, think a dihedral torsional scan that after full rotation recovers the same value, and you have 0 to 360 degrees, then you can basically solve this boundary condition problem by enforcing that the left segment to this polynomial is this one, and the right segment to this polynomial is that one. So they're basically connected on a ring. So the main message here is, depending on what kind of boundary conditions you pick, your polynomial and your interpolant is going to look vastly different. And maybe surprisingly, not only at the boundary, but also further in. So here you see they differ, and they still differ over here, even though that's pretty far away from the boundary. So one of your problems in the exercise is going to be one numerical example where you see how large this deviation can be depending on how the boundary value looks like. Because if you have something that is highly dependent on this outer point, then of course you can imagine if I move this point just a little bit upwards, then the rest of the curves are going to change. It's not like it only changes the curve in the first interval. And this way you give more weight to these outer points than you give to the inner points. That's why the boundary conditions are very relevant in those cases. There were C-splines. Let's have a look at the B-splines. The picture on the right you already know. It's the same picture we had at the beginning, explaining this smoothing or regularizing factor S. And the nice thing is the code looks nearly exactly the same. So rather than calling psi.cubic spline, you call psi.univariate spline. And you can give it an S argument over here, which relates to this smoothing factor on the right. And it's called in the very same way. You get a new object, B-spline, which you can just call as if it were a function. So this means that the interface, the way how to deal with it, is practically the same. It just helps to keep in mind what the underlying difference is between cubic splines and B-splines, and in particular the smoothing aspect of things. By default, these are cubic B-splines, because of course the B-splines come in different orders. We have discussed that. You can also specify what kind of order you'd like to have, but please keep in mind too high an order gives you a better chance at numerical issues. So keep in mind this B-spline thing is an object, and the B-spline thing, just as the C-spline object, has functions for the derivative and the integral and root finding. So this can be quite helpful if you want to, for example, find the minimum of some function. This brings me to our use case example. So what I have here is one bond stretching. This is N2, and the idea is, if I want to figure out the minimum position, so what's the most stable bond distance, then the problem is I can use an optimizer. And you implemented your own Newton optimizer, so you have seen how this can take a few steps. You have seen the Rosenbrock function, and where you get quite a substantial amount of steps in order to find a minimum. And this means that using an optimizer is of unknown cost. I don't know how many steps I have to take in order to get to the minimum. I don't know that beforehand. Now, what if I just want a quick estimate that tells me something about where the minimum should be with the fixed cost? So no matter how this potential looks like, that it has a fixed cost of function evaluations. So here we have 1, 2, 3, 4, 5 function evaluations. So that's a fixed cost, and any optimizer is going to take significantly more steps, which we'll see on the next slide. So what if we look at those 5 points? Sorry. So this is what we do here. So we have PySCF, the code that you've seen in the other lectures as well. We have this one function that calculates the energy of N2 if we have a fixed bond distance. So again, this is the molecule definition of 1 nitrogen in the origin and 1 nitrogen displaced at a certain distance along the z-axis. And again, we have to specify what kind of calculation we'd like to do. That's why we have the basis set over here and our computational QM method. And what this function returns is just the energy. So it creates the molecule, it runs the calculation, and it returns the energy. So now, if we do that, what we have is this all the points at which we'd like to evaluate that function, and we just build a new list ys that contains the energy of each of those bond distances. So then we have our two arrays, xs and ys, that contain the data points here in that plot. All right, now we have the data we would like to interpolate. So if you merge this together with what we had on the previous slide, then here we load scipy interpolate, and we can either build a C-spline with scipy interpolate cubic spline, or we can build a B-spline. This actually should be a B-spline. I'm gonna correct this online and give you an updated slide on that. So this here is a B-spline because we call the univariate spline. And this way we have a new object. And as I mentioned before, we can get the derivatives. So if we interpolate things, we can ask this object, give us the derivative and tell us where this derivative is 0. So where are the roots of the derivative? That's beautiful, because then what we have here is the object dot derivative just gives us the derivative. It's easy because it's a polynomial. And then we can call roots, and it's going to give us the list of all, well, roots of the function where it is 0. Now for the C-spline, we get 2 numbers. One is at 1.08 angstroms, and the other one is at 1.75 angstroms. But the 1.75 is outside of our domain. And as you've seen in yesterday's lecture, this outside region is not very well covered by polynomials. Cubic splines being polynomials, this means that it's basically undefined what happens outside of those regions. So we know that the minimum corresponding to this minimum over here, so for the orange line, is at 1.083 angstroms. And for the B-splines, we only get one minimum, which is fortuitous, but the minimum is at 1.085 or 6, and that's the dashed green line on top of the orange. So these would be our distance estimates that we get just from interpolating those 5 points. And now we can just say, all right, what would be the scipy optimize answer to this? It's the minimize function over here with the energy function from the previous slide, and we need to give it some starting guess, and I give the guess of just 1 angstrom. And you see it's 24 function evaluations to get to the true minimum, which is at 1.089. So these two minima are not perfect, but they're pretty close, given the fact that this is almost 5 times as expensive as these estimates. So that's why interpolation can help you in those regards to give you more efficient evaluations. For example, what you could do in a production environment, if you want to do actual research in this direction, you could say, I calculate my 5 points for some guessed bond distance. I figure out what is the estimate of the minimum, and then I use the minimizer and let it start from that minimum guess, which is going to be much faster because your guess is better. You're basically saving all the time that the optimizer needs in order to move from here to here if you can place it already quite near to the minimum. So that's what's commonly used in actual calculation studies. Python can do the 2D case. I just want to quickly mention that and give you the name of the functions that you can use for that. Since it's rarer in practice, I don't want to go into detail on that. So if you want to have splines on a regular grid, so where all points are rectangular, then you can use this class in scipy optimize, rect bivariate spline. If you don't have that, but if you rather have irregularly spaced points, then you need to check out this function, which comes in 2 flavors. You can either have the linear mode, which is effectively interpolating between nearest neighbors. That's fast but not smooth. Or you can have the cubic mode, which tries to map cubic splines in 2 dimensions. That's going to be slow, but at least smooth on first derivative. So that's what I want to talk about on interpolation in Python. This being the last lecture on the numerical part of the series, I would also like to mention a few other tools that might come in handy, or in other words, things that I would have liked to know about earlier in my work. And this is effectively 3 concepts. I would like to, in the following minutes, give you an idea on what kind of tools you can use with Python in order to solve problems which are common in a chemistry environment, regardless of whether you do theory or experiment, but which could be helpful in automating a good part of the mundane works that you have to do in day-to-day life. And this is always geared towards Python, so in all cases I will show you how to do that in Python and why you can. So the 3 things I just want to mention and which are not going to be part of the exercises, but maybe something that is helpful for you to take away, genetic algorithms, automatic differentiation, and symbolic algebra in Python. Genetic algorithms, we mentioned that in the optimization lecture, so that this exists, and I promise that we're going to talk about that in a little bit more detail, which we'll do now. And it's particularly helpful if you have a higher dimensional optimization problem that you need to tackle kind of in a black box fashion. And this is available in scipy, it's a common Python library, and DEAP, an uncommon library, where DEAP is more advanced and gives you more low-level insight into things, and scipy is more the high-level picture. So effectively, whenever you have an optimization problem that needs to work, let's say hundreds of times, thousands of times, millions of times, without looking at each and every optimization, whether it converges to something useful, then genetic algorithms are typically the way to go. I will explain what's the core idea behind and show you an example implementation. Automatic differentiation is a picture or a method if you don't have real derivatives. Imagine you have some function, and this function is maybe defined by some Python code. Then you don't need to sit down and manually derive what would be the derivative expression and then program the derivative expression yourself. You can make use of a library called autograd. And there are also others, but I like this one, of this library, where you basically, you can write one function in Python, and then you can ask autograd to derive that function, so that Python function. And this works with for loops, if statements, whatever. You get proper derivatives of that. And that's pretty convenient and helps to reduce errors. If you need derivatives from somewhere, then this gives you reliable numbers. And the last thing I want to talk about will be symbolic algebra, where the idea is changing equations or deriving equations, in particular if they are lengthy, can be a pain to do by hand, and it's error prone. Now, you probably know that you can do something like that in Mathematica or MATLAB or whatever computer algebra system you might prefer. I just want to show you that you can do that in Python as well, which is nice because that interfaces with NumPy and the rest of the Python ecosystem. So you can build long mathematical expressions directly in Python code and make this callable Python function within with the help of NumPy. All right, let's talk about genetic algorithms. So we talked about the problem class in the optimization lecture, where genetic algorithms are helpful. Most importantly, if you want to find a minimum, but you have no direct idea of where it is in the search space. And genetic algorithms are inspired by evolution, where you have a certain set of terms or expressions which are all following that particular picture and have a meaning in the optimization environment. So the idea is you come up with some random solutions, and then you try to combine solutions which are good and then generate more random solutions close to those that have been proven to be good, whereas you discard all those which so far were not a good solution to your target function. And this is done, the vector describing the solution, so that's what we called x0 in our optimization lecture. That's a genome in genetic algorithms. And now what you have is you have a set of those genomes, and this you call the population. So for example, typically you have maybe a few hundred different solutions, whether they are good or not, so whether they're close to a minimum or not, doesn't matter. First of all, you have a certain set of random such populations. And this is the population, and then you have generations, meaning that every time you change something in the population, you drop a few solutions that were not close to the minimum, and then you create new solutions that are hopefully better than the ones you had before. And you do that by either mutation, so this means you have some random solution vector and you change it in a certain way. For example, pick a random variable and make it slightly larger or slightly smaller. That's a mutation. And this takes one genome and makes it one new genome. The alternative is the so-called crossover. So this means you take two solutions and you make one new solution that combines features. So for example, take the first 5 entries from the one solution and the rest of the entries from the other solution and try to see whether this improves your optimization. So that's basically what you have with parents and children. And then the selection mechanism is inspired by survival of the fittest. So the fittest to adapt actually, but the comparison doesn't carry that far. So it's called a fitness function, which is just your target objective. So these are the terms, and the basic idea is you basically are smart about the way how to generate random solutions that are good estimates for what you want. And it's often combined, as I mentioned in the optimization lecture, it's often combined with gradient search. So once you have some new good estimate, you just go towards the minimum in those. So in order to make use of this, you need 3 things. You need a way to evaluate which of those solutions is better. And that's your fitness function. So for example, this could be, if you have a function that you minimize, this could be the residuals. And what you also need is some description of the solution. It does not have to be the solution coefficients x0 that we have in our optimization lecture. It just has to be something that at least allows us to derive a unique solution. It's often common. It's common to pad this solution vector and to add a little bit more to call it degree of freedom, because that typically makes the mutation a little bit more efficient. So, but you need this representation in a simple case. It's just your solution vector. And you need a way to figure out a random valid solution. So you need to be able to create random representations of some solution. So if you have this, then you can use this kind of algorithm. And if you want to make this very efficient, then you have to worry about these details. If you just want to make use of the concept, then there are typically default values for all those operations that work sufficiently well. So effectively, if you want some quick automatable answer, then genetic algorithms are probably the way to go, but they are not in a stage where they are purely black box and work in any imaginable case. Often you have to fine-tune them. So this is typically helpful if you have something like not terribly high dimensionality, but maybe up to 20, 30 dimensions, and you have a little bit of human time available. So this really only pays off if you have very large number of optimizations that you'd like to do this way, where you can't check each and every result. That's where genetic algorithms typically shine. So it's an upfront development time investment to make life easier later on. Something that genetic algorithms are particularly bad at is classification. So don't try. Okay, so how and why would we do that in Python? So this is one example. Please look at the figure on the right first. So what we see is 3 peaks. And imagine you care about line positions. So you have, say, an experimental spectrum that might look something like this, and you have narrow peaks. And here you see you have 2 peaks. Here's the third one. and you would like to know which of those peaks are where they are and what's their y value, so what's the maximum height. And if you know that there's going to be 3 peaks, then you can also say, I just use my scipy optimize, I've learned about that, so I just use my BFGS and life is happy. The problem is that this is very narrow. So if I'm slightly off with my position, then I will never have a way where BFGS gradient-wise on this plane over here moves the peak to that side. There is just simply no gradient in those things that optimizes the residual. It just doesn't exist. So let's briefly talk about how this is generated. So here we have a function that takes the scale and the position. So the scale is the height, and the position is the x-axis value of that, of each of those peaks. And then say we have the positions B, D, and F, and we have the heights A, C, and E. And we calculate just the regular Gaussian centered with some line width around this individual point. So if we call the function, that then is going to calculate exactly this thing for these parameters A to F. And then we can get our residuals, which require to calculate the difference to the true values, so to the y-as values that we have here. If you do that with minimize, then you've seen how this works. So you use scipy minimize, you give it the residuals function, you give some initial estimate of those positions. For example, I could guess it's 10, 20, and 30, and then I optimize that. Now the problem is, this won't converge. And the reason is that there's just plain no gradient in this position to make things better. It's equally worse wherever your peak is. And you're never going to find these narrow minima. However, if you use a genetic algorithm, then there is a little bit of randomness to it. And this is what in scipy optimize, the function differential evolution can do for you. So again, you give it the function. It's the same as for BFGS. You give it the arguments. It's the same as in BFGS. And you also give it bounds. So you say for each of those values, what's a reasonable range that it can expect. So you can say the intensity is somewhere between 0 and 1, and the peak position is somewhere between 0 and 100. And if you run that, then what you see is that BFGS uses about 1,100 evaluations, depending on how many evaluations you give it. But in the end, it's not perfect. It basically misses these 2 peaks. Because then the first peak that we have guessed is at 10, the second peak is at 20, and the 20 peak is within this domain. So it runs into, there's a downhill gradient that BFGS can use. But the 10 and the 30, they are outside of this domain. There's just no gradient. They're never going to move to this peak, and that's why this feature here is completely missed in BFGS. That's the residual over here that is substantial, whereas the genetic algorithm has a much better accuracy, even close to machine precision on this. But of course, it used much more evaluations than BFGS. So you pay for the randomness to some extent, but then the idea is if you're clever about the way how you choose those individual evaluations, then genetic algorithm is not that expensive. So if you want to do that, then as I mentioned, this is what you can do with scipy. If you want to be more closely related to this thing and have very special strategies on how to combine solutions such that the combined solution is still sensible, then you might want to check out the DEAP library that we had on the previous slide. Okay, that was a genetic algorithm. Another concept I would like to show is the automatic differentiation. And the central idea is that any code you write is just a function. I mean, it takes some arguments and it gives some answer. So that's exactly the definition of what a function is. And you can keep the statements that program has executed, and just apply the chain rule, because every time I do something, I'm just wrapping my result that I get and then do something else with it. So it's a convolution of different functions, and I can just apply the chain rule from that and get my derivatives. Now, just apply the chain rule is where the dirty details lie, and that's why you want to use a library. But it's fairly easy. If you look at this function over here, so we import a different flavor of NumPy. So we use autograd.numpy, which means we just write NumPy code as we used to, but autograd is calling NumPy in the background, but it's also keeping track of what we did with NumPy. And then we also import the element-wise gradient, meaning for any vector, we get the gradient individually for every component. So let's imagine this function here, xs, which is the one we want to integrate, to differentiate. And what we do is we just take some result vector, which is all zeros, and then we have this for loop. The for loop takes some sine function, divides us by the input, and then returns the result. So this is not a mathematical function that you have written somewhere or just concatenated NumPy calls. You can just write regular Python code as if you would do it, and then say, what's the gradient of this function here? And that's exactly what you get. So here we can plot the function xs, that's the blue line over here. And then we can say, give me the gradient of this function. That's what this egrad does. Give me the gradient of this thing and evaluate it at all those positions. And then you get the derivative while never having thought about what's the derivative of this and how to implement it. And then, of course, you can get higher order derivatives by just, well, taking the derivative of the derivative. So this is then the second derivative in the picture. And again, you have never thought about what's the functional form of this and how to write this. So this is pretty helpful either in the machine learning context, that's where it's most commonly used, particularly in the context of neural networks and training, because this gives you a way to get derivatives with respect to all input parameters, most importantly the weights of the network. It's also helpful if you want to do an optimization of a Python function for which you don't have explicit gradients, either because you haven't thought about them or because it would be too much effort to actually think about them. And this means you can forget about numerical differentiations, finite differences, but rather use this because that's exact. And the beauty of it is you just write your regular, plain and simple Python code as you always have done, and you get your derivatives for free, which is particularly helpful if you have complex code, because then properly deriving this by hand may or may not be something that you can do error-free. So in particular, I have to say, is not the fastest thing. So the evaluation here is fast, getting the gradient isn't. So no free lunch theorem is added again. And it tells you that this is good if you have a few functions that you'd like to differentiate. This is awful if you have many functions you'd like to differentiate. But it's, in all cases, it's still better than finite differences. All right, now for the last thing, symbolic algebra. The idea is we all know functions, and we love the beauty of the mathematical expression, but it's painful to do that in code. I mean, how do I simplify a function in code? And often if you just read a paper and it's a mathematical expression, then you can think about how to write that in code. And one way of doing that, in particular if you have to combine it with something else, is to let the computer generate the code. So as long as you know how to write something in, say, LaTeX, or in plain simple functions, as for loops or something of the like, then sympy can generate proper fast Python code for this. So the idea is you have this module sympy, and every variable, so every symbol in your equation, is captured by a certain variable. And then you can say, I just, again, have my function and I write some for loops, and I add the special sympy sign function of that variable. Then what you see is what you get is exactly this, this expression. And Jupyter notebooks are going to render any sympy function with LaTeX-like representation. So you can look at it, it's nice, more pretty than the Python code. But now the beauty is you have this thing, so you can say what's the derivative thereof. You can just call sympy.differentiate of this. And there what you get is precisely the derivative. And this way you can say, I'd like to implement this, and then give me my analytical derivative, so no automatic differentiation, no finite differences, just what's the result, and then you can transform this. You don't not only have the mathematical representation, you can also transform it with this function called lambdify. It's hard to explain why it's called lambdify, but bear with me. This function, or this variable over here, this way, becomes a callable function. So similar to the way what we had with the C-spline and the B-spline earlier, you can just give it the value, it's going to evaluate that value at that point. But this L over here uses numpy, so it's definitely fast. So again, this step over here, this lambdify, it's going to take some time, but the function call afterwards is basically fast. So this means you can have one Python code where from the mathematical derivation of your model, of your logic, of your fit function, you do everything, even the algebra part in Python, and then you say, please give me some numpy function for that, and you get all your derivatives symbolically, and you can evaluate them easily in numpy. And the reason this is called lambdify is because lambda functions are unnamed functions. So you can have a function definition in Python, and usually you have to give a name, but there are conceptually functions where you don't give a name because you only use them temporarily, for example, and this is called a lambda function. So lambdify means give me some unnamed function. Okay, so with this today we have seen interpolation and how to do that in Python and NumPy environments. We have talked about B-splines and cubic splines. We've talked about the regularization aspect of things, so when to use it and why to use it and how to deal with noisy data. And you have at least briefly heard about 3 other tools that, depending on which direction you go during your studies, might be useful in order to be more efficient and have more fun in solving day-to-day problems. So with this, I'd like to thank you everybody